Hey there, Chem Scholars. I'm going to try this again. I spent about 15-20 minutes recording and it didn't work. Trying again, just for you. Yeah. All right, so we're doing what section 3 here is called compound calculations. Some of it's familiar. We're familiar with the idea of molar mass, sprinkling in a little bit of that nomenclature stuff, and then we're going to learn a few other little nuances of it. All right. So first of all, let's talk about molar mass. You know how to find molar mass, but to find molar mass, you need to know your nomenclature. Okay. So nitric acid, it means 8, so we're looking for a nitrate ion, and which has a -1 charge. So we need 1 hydrogen, HNO3. All right, so then that means that we're going to be adding, let's see if I can estimate this right, 1 hydrogen, 1 nitrogen, and 3 oxygens, right? Ones aren't written here, but we know that that means there's 1 hydrogen, 1 nitrogen, 3 oxygens. Okay, so now I just need to figure out where the end of this is. Actually, that would be the easier way. And say, all right, I go to the periodic table. Hydrogens are 1. 1 times 1 is 1. Nitrogens are 14. 1 times 14 is 14. Oxygens are about 16. 3 times 16 is 48. 48 plus 14 plus 1 gives us 63 grams per mole. All right, let's talk about aluminum carbonate. Okay, so aluminum is a +3 ion. Carbonate is CO3. It's a -2 ion. All right, so we should end up with something like Al2CO3 3. All right, so now we got to be careful with those parentheses, right? Because we got to make sure we get the right number of pieces here. Okay, there should be 2 aluminums, there should be 3 carbons, there should be 9 oxygens. Now we bring it down and go to the periodic table. Okay, aluminums have a molar mass of about 27. There are 2 of them, so that's 54. Carbons have a molar mass of 12. There are 3 of them, that's 36. Oxygens are about 16.0. There's 9 of them, that's 144. So now we add up all that, and we get around 234 grams per mole. All right. Damn, no L in mole. Gotta go to mole. All right. All right, let's do ammonium phosphate. So ammonium is an NH4. It's a +1 ion. Phosphate is PO4, and it's 3 negatives, so I'm going to need multiple ammoniums. So we have NH4 in parentheses 3, PO4. Okay, so now we break it down. I got to remember to distribute. So there are 3 nitrogens. There's going to be 12 hydrogens. There's going to be 1 phosphorus. And there's going to be 4 oxygens. All right, so now I go to the periodic table again. For nitrogen, we already said the molar mass is 14. For hydrogen, we already said it's 1. For oxygen, we already said it's 16. So the only one really looking up is phosphorus, which is about 31. So there are 3 nitrogens. 3 times 14 is 42. There are 12 hydrogens. 12 times 1 is 12. 1 phosphorus, so that's 31. And 4 oxygens, that's 64. So now I add that all up, and I get about 149 grams per mole. All right, now we have oxalic acid. It's another ick. Ick means 8. The oxalate ion is C2O4, and it's a -2 ion. And since it's -2, that means we're going to need 2 hydrogens in this acid. Okay, so it's H2C2O4. All right, so as I just said, there are 2 hydrogens in it. There's also going to be 2 carbons, and there's also going to be 4 oxygens. All right, and we've already found all of them before, so hydrogens are 1, carbons are 12, oxygens are 16, so 2 plus 24 plus 64, and that gives us about 90 grams per mole. All right, so that's the review part. That's molar mass with the sprinkling of that nomenclature thrown in. Just love the taste of that, don't you? All right. Anyway, we're going on to nitric acid. And now I'm talking about something called percent composition. All right. Composition means what something is made of, okay? So when we talk about the composition of a compound, for example, nitric acid, we're saying it's composed of hydrogen, nitrogen, oxygen. But percent composition is implying how much of it. But it's not percent in terms of how many atoms. So it's not saying that there's one hydrogen out of every 5 atoms in nitric acid. That would make some sense, but that's not the way it's measured. It's measured by mass. So some people call it actually percent by mass, or mass percent composition. Okay? I was always taught it's just percent composition, so you're stuck with me. All right? So again, we know nitric acid is made of hydrogen, nitrogen, oxygen. But what we want to know is what percent of the mass of nitric acid is hydrogen. Well, we can do that by working right here with the molar mass. We figured out that every mole of this is 63 grams. So out of that 63 grams, 1 gram of it is hydrogen, right? Because this part was hydrogen. So the hydrogen, very specifically, is 1 out of 63, or 1.6%. Let's talk about the nitrogen. It's 14 out of every 63. So that's 22.2%. Okay, let's talk about the oxygen. All right, the oxygen made 3 times 16, or 48 out of 63. So that's obviously the biggest part of this. So 48 out of 63 is 76.2%. And I could have found the oxygen at this point a different way, right? Because the sum of these percents should be about 100. Round off differences aside, it really should be exactly 100. So 1.6 and 22.2 is 23.8. If I subtracted 23.8 from 100, I would get 76.2. All right, I'm going to say, pause the video. Try the next 3, see what you can do for aluminum carbonate, ammonium phosphate, and oxalic acid. I'm going to keep going now. So, aluminum carbonate, we're going to start with aluminum. There were 2 of those, so that was 54 grams out of the 234. And that's 23.1%. Okay. Where am I? Carbon, there's 3 times 12, or 36 out of that 234. That's 15.4%. And I'm just going to go out and do the whole thing. So the oxygen, 9 times 16 is 144. So the oxygen is 144 out of 234, or 61.5%. Okay, so that is the percent composition. Now sometimes I'll just say, what is the percent of oxygen, or percent composition of oxygen in nitric acid, aluminum carbonate, ammonium phosphate? So you don't have to do all the elements, but if it doesn't specify an element, then you're doing it for all of the elements. All right, so ammonium phosphate, we got 4 elements this time, so we're going to start with the 3 nitrogen, so that's 42. So we're starting with 42 out of 149, that's 28.2%. Then we go on to the 12 hydrogens, 12 out of 149, and a little bit smaller percentage there. We're going to be at about 8.1%. The phosphorus is 31 out of 149, okay, so that's around 20.8%. The oxygen makes up the rest of it, but again, I'll just do the math way and go 64 out of 149. I guess they're both math ways, but anyway, or 43%. Now notice when I add up these, okay, 0.8 plus 0.1 plus 0.2, I get a 0.1, I get 1.1. I'm actually getting 100.1 when I add them up. That's because of round off difference. So I said it should be about 100. 99.8, 99.9, 100.1, 100.2. Really, you should only be off by maybe 1/10. But, if you're in that area, it's probably reasonable. Anything more than that, double check your numbers on the calculator, because we all make mistakes once in a while. All right, oxalic acid, we're going to start with hydrogen, which was 2 out of 90, or 2.2%. All right, and then we have, oh, hey, I didn't mean to do that. All right, Then we have the carbon, which was 24 out of 90, or 26.7%. And then we have the oxygen, which was, again, 64 out of 90, so we get 71.1%. So that's all that percent composition is. It's really a pretty simple thing, especially if you do your work out for molar mass, then it's all right there. We don't have to really do it all again. All right. One of the things in science that you should know, though, is that when we do operations, we also learn the reverse operation. You know, in math, you do it too, right? You learn addition, you learn subtraction, you learn multiplication, you learn division. Okay? We talked about converting moles to grams and grams to moles, moles to atoms, atoms to moles. Same thing. We always reverse things. All right? So I'm mentioning that now because now we're going to talk about, we took a formula, well, the name, but essentially the formula, and use that to find these percents. Now we're going to take percents and work back to find formula. But specifically, we have to find something called the empirical formula. The word empirical means simplest, and we mean, in this case, whole number ratios. Okay, so when we talk about empirical formula, we want simple whole number ratios. No decimals, simple numbers when possible. Now, keep in mind, not all compounds are written as empirical formulas. They're really all called something called a molecular formula. We're going to come back to that later or tomorrow, depending on how the time of this video goes. Okay, so notice here, there's a ratio of 2 to 2 to 4. That's not simple whole number. That is not empirical. Okay, empirical would make it 1 hydrogen, 1 carbon, and then we would throw in 2 oxygens. That would be the empirical formula for oxalic acid. And you might be saying to yourself, why would I want to know the empirical formula then if I know the actual formula? Great question, okay? And the reason is we don't, okay? It's a stepping stone. We have to find the empirical formula before we can find the other one. The empirical formula is just easier to find mathematically and also from a laboratory sense, okay? So we find the empirical first, and that's going to help us to determine what the actual formula is. So we're going to just not worry about what the actual formula is. We're just going to find these empirical formulas. So in part A, we're told that this compound is 80% carbon, 20% hydrogen. 80% of what? 80% of anything. We could choose any number we want, okay? It's a percentage. No matter how much of the sample we have, 80% of it should be carbon, 20% should be hydrogen. So we could assume we have 2 grams total. We could assume we have 1,000,000 grams total. But since it's percents, I always tell my students that we are going to assume that it's 100 grams. Okay? Why? Well, percents out of 100, right? So 80% out of 100 grams means that we know we're going to have 80 grams of carbon. Oops, copied a little too far there, but bear with me. Okay? And that would mean we have 20 grams of hydrogen. All right, so how does mass help me? Well, remember we did our conversions and we went from mass to moles to atoms. Well, moles and atoms are proportional, right? A mole represents a set number of atoms. So if we figure out how many moles there are and compare those ratios of moles, it's going to be the same as comparing the ratio of the atoms. Okay, so long story short, we're going to convert to moles, and that's what I started doing here by saying, if we look up the molar mass of carbon, 1 mole of carbon is about 12 grams, and 1 mole of hydrogen is 1 gram. Okay, so that's just molar masses of them. All right, so I divide that out. I get 6.67 moles, and I get 20 moles. All right, that does not seem like a simple whole number ratio. Well, it's not. We have to simplify it. Okay, we just got a ratio. Now we go to simple whole number. When you are simplifying in math, like we did with the oxalic formula, where did I do that, oxalic acid? When we simplified this to 1 to 1 to 2, we divided everything by 2. Right? You have to figure out what to divide by. So what we're going to do is divide by the smaller number. So we're going to divide by 6.67, and then we're going to divide by 6.67. Okay. So when I divide here, Obviously, 6.67 divided by 6.67 is going to be 1. When I divide 20 by 6.67, I'm going to get a number very close to 3. And again, it's got to be really close to a whole number. You're off by a few hundredths or something like that, that's fine. Okay, shouldn't be off by tenths, it should be hundredths. Okay, so again, is 20 to 6.67 the same as 3 to 1? Yes, it is. Okay, so that is a simple whole number ratio. And so that's telling me how many carbons and how many hydrogens I should have. And so my empirical formula is 1 carbon, 3 hydrogens, or CH3. Okay, so that's the process for empirical formula. Okay, we're going to assume that the percents are out of 100, so that gives us the grams. We're going to divide by the molar mass of each element, and then we're going to simplify our ratio. All right, so try B. I'm going to explain a little bit more about it. Okay, I'm not going to explain. I'm going to go over it. You pause the video and go over it. Yeah, whatever. I can't speak. It's a long day. Anyway, 27.29% carbon. All right, so that means we have 27.29 grams of carbon, and 72.71% oxygen means we have 72.71% grams of oxygen. Blah, blah, blah. All right, so carbon's molar mass is 12, and oxygen's molar mass is about 16. All right, we divide it out. And so we get 2.27 moles for the carbon, and we get 4.54 moles for the oxygen. We're going to divide by the smaller number. So in this case, for carbon, it's 2.27. We divide 2.27 by 2.27, we get 1. Divide 4.54 by 2.27, I get 2. So there's my empirical ratio, 1 to 2, which means my empirical formula is CO2. Now, you might be saying, that's got to be carbon dioxide. It doesn't have to be, but it could be. Again, this is the empirical formula. We don't name empirical formulas. We name molecular formulas. So when we get to molecular formula, then we can talk about the name of the compound. Up until then, we don't make assumptions, okay? It's just not always going to work. Now, I wanted to go through C, and since the work is already there and I forgot to white it out, we'll just go with it right now, okay? Because there's something different that happened here. So I took the 25.94% of nitrogen, made 8 grams. I took the 74.06% of oxygen, made 8 grams, divided by the molar mass of nitrogen, divided by the molar mass of oxygen. I got 1.852. I kept an extra digit in there because I wanted to make that point, and I'm glad I did because I would have forgotten. You cannot have too many digits for this. So this is not a sig fig thing, because remember, we're trying to get the simple whole number ratios. So in the end, it should be very simple numbers. Okay, we're not going to deal with decimals. When you're writing this down, it is very important that you not keep rounding off, okay? Because if you made this 1.9 and 4.6, it's not going to work as well, okay? So you keep extra decimals or keep it in your calculator and just do it in there, that's fine, okay? But be careful about that. In any event, so when I get these 1.852 moles of nitrogen, 4.629 moles of oxygen, I divided by the smaller number, 1.852, and I got a 1 here. And when I divided here, I got about 2.499. Well, that's 2.5. Keep in mind we were making assumptions. We made an assumption about mass. That one's not an issue. But we also, when we divided by the smaller number, we were dividing by the smaller number, assuming that there would be 1 atom of that. Well, not all formulas have 1 atom in it, okay? Again, going back to that oxalic acid, there were no 1s in here. It's a 2, 2, and a 4, okay? We can't assume that there's 1s, okay? We did, and it's okay. But if we make the assumption, then we have to adjust for it. And the problem was that I came up with a half because of that. And that tells me I should have doubled, right? The way you get rid of a half is by doubling. So I doubled both of them to maintain the ratio. 1 to 2.5 is the same as 2 to 5. So my empirical formula really should be N2O5. All right, so once in a while you'll see those halves. It's possible that you could see a third or even a quarter. Those are rare. Halves come up a bit. Okay, the other fractions, not so much. Okay, but just be aware. Okay, again, when you're dividing at this point, you should be very close to a whole number. If you're not, then you got to think about what fraction you're closest to. All right, let's not bog down too much on that. All right, try part D, pause the video. I'm going to go on. All right, so we're assuming 100 grams, so we're going to say we have 3.25% of it would mean we have 3.25 grams of hydrogen. Okay, and 19.36% would mean 19.36 grams of carbon. Okay, let's see if I can squeeze this in. 77.39% would mean 77.39 grams of oxygen. All right, so now I'm gonna do a little, save myself a little pasting in here. Okay, so the oxygen's molar mass is 16, the carbon's molar mass is 12, and the hydrogen's is 1. All right, well, that one I can do in my head, 3.25 moles of hydrogen. Okay, now here, let's see, 19.36 divided by 12. We get around 1.61 moles of carbon. And 77.39 divided by 16. We get around 4.84 moles of oxygen. Again, I probably should have kept an extra decimal or so, but I think I'm okay where I am at this moment. So the smaller number is the 1.61, so I'm going to divide this by 1.61. I'm going to divide this by 1.61. I'm going to divide this by 1.61. All right, so 3.25 divided by 1.61. I know it's going to be close to 2. I'm just going to check to see how much. So 3.25 divided by 1.61. I get 2.02. All right, so again, only off by a few hundredths. That's good. We're going to call it 2. Okay, obviously that's 1. And I know that 16 goes into 48 3 times, so I'm sure that 1.6 goes into 4.8 3 times. So there's my ratio. So that means my empirical formula would be H2CO3. Now that does seem to be something familiar to me. Maybe not to you, guys, but again, it's an empirical formula. Not going to worry about that yet. All right. I'm not going to worry about going over 18 now. I think that's enough of those. Okay, I'll share the answer with you. But I do want to talk at least for a moment about molecular formulas. All right. You know what? No. I'm going to save that as a do now. We're going to stop there. I think that's enough for this right now. I want to make sure you understand this. So don't forget you can go work on the homework and try those. The problems generally match up reasonably well, so you should see where we're at in that. All right. I think a 23-minute video is more than long enough. You've heard enough of me for now. Ciao for now.